welcome to our podcast today, Quantum Jollof podcast, where we interact with several scientists from Africa, from Nigeria. They tell us about their journey and how they persevere to get to where they have gotten today. Our guest for today is Dr. Ajayi Samuel. Is a freshly minted PhD, and I want to be like him one day. Actually, so he holds a first class degree in physics from University of Ibadan in Nigeria. Then he has masters in radiation and earth physics from University of Ibadan in Nigeria as well. And he's a freshly minted PhD graduate from Florida State University, where he studied nuclear physics. He's husband of his beautiful wife and the father of two. And I know he's a pastor and he's a believer of Christ. That's an addition to the bio.
I think is because his name is Samuel Ajayi, and then the last part you forgot was Samuel Ajayi
Crowder.
Yeah, there's Ajayi. I've received that question a lot of times. Are you related to Samuel Ajayi Crowder?
Dr. Sam, I'm not going to call him Crowder because you're welcome to our space today, and we are so glad to have you in our space, and we are very privileged to be interacting with you today. Thank you for accepting our invitation.
Thank you so much. I really appreciate it. Thank you.
Yeah. Before we go to the questions that we have for Dr. Ajayi today, actually, seeing someone that studied nuclear physics is mind-blowing for me, because one of the things is that the last time I went to the US Embassy to try to get a visa, I studied biotech. I still studied biotech. And then the question they asked me is, you did biotech? I was like, yeah. They say, are you making bombs? I was like, I'm not even doing nuclear radiation or whatever. I didn't even know that I would be able to eventually ask someone that does nuclear physics. But that's by the way. But Wale, I want to ask you a question. When you hear about nuclear physics, what comes to your mind? Imagine you are a US consular and someone says you are going to study nuclear physics in the US. Would you be scared to? This person is from Nigeria.
Yeah. Can you see my background? Of course, it's going to. The person is making bombs. Maybe it's otherwise, but Dr. Sam will clarify it to us today.
Yeah, it's going to because nuclear physics, and me, I'll be like, hey, you just go to the lab. You are a pastor and you are making bomb. That's quite, that's quite.
Yeah.
No, it's funny that the first thing that comes to the mind of people when they hear nuclear physics is bomb and the likes, but nuclear physics is a lot more. There are different aspects to nuclear physics. Remember, nuclear physics is studying the nucleus, right? In terms of you want to know the energy potentials and all the different things that come into place with it. So there is a theoretical aspect of it, which has to do with a lot of calculation, a lot of modeling, a lot of simulations, lots of writing programs and the likes. And there is the experimental part of it, which I do. And even in the experimental part of it, there are different areas, okay? Like you have the nuclear structure, you have the nuclear reactions, you have fission. That is the part that actually deals with bombs and the likes. You have fission reaction, you have fission, people are even doing fission. That's to do with nuclear reactors too and the like. So there are different aspects, and there is even the application aspect too, right? Remember, you have theory, you have experiment, and then you have application. So many times there are even separate people who do the application. For example, I won't build anything, right? I can only study reactions and see what goes on and the likes. And then those who do application will do application. So even if you see every of these things that you see being applied, it's just like technology too. There are people who will study the feasibility of something taking place. Let's say those who work with what do you call it now? Crystals, who grow crystals in the lab and the like. There are those who will do that in local just to see which one is feasible, how to grow it better, blah, blah. And when that is gotten, that is perfected, There are those who will apply it to the field, maybe those who will now build chips, who will use it in, but based on what the scientist has done, basically. So my research is to be able to do the experimental part of things and compare with theory.
Actually, we are going to get to that part. So let's go step by step so that.
So I'm not making bombs. That's just
yeah. All right. The first question I have for you today is like from Nigeria, and like many of us, I'm like 50% sure that you came from a very humble background. And now you are here today, probably a first generation PhD student or second generation PhD student graduate. Can you tell us about your scientific journey, how you left Nigeria, how you got here, how you are able to like get into nuclear physics? Now you are a PhD graduate. Can you like in few words, can you try to like tell us about your journey?
It's been quite a journey. I would say I'm even a first generation college graduate because that is what I am. And then I just pushed it to that limit, which is PhD, obviously. So it's taking a lot of dedication, a lot of hard work, of course, a lot of perseverance. That's the word I'm looking for. It's taking a lot of perseverance because coming from that background, thank God for my parents who are very passionate about education. That's just what they are really passionate about education. They push you, and then I was able to, and I had people around me, friends around me, who are also passionate about education too. So it's just like we keep pushing each other. And during my undergraduate, of course, I won some scholarships during my undergraduate days, which helped with tuition and the like. You know, in coming from such a background where it's tough for even your parents to pay 30,000 naira tuition, 50,000 naira tuition, and the like, 19,000 tuition. I remember when I collected one scholarship, then 50K. That was the end of my first year. And I went back to go and pay my mom, my dad, and mom back the tuition they paid for because over Johnny, you know that kind of thing.
Yeah.
It's all this dreams, all this contribution and the like, just to pay them back. Like, and then I kept maybe 10K or something. I can't remember for myself, 15K for myself. Even the first laptop I bought, you know, the struggle. I was working. I was on campus. I was teaching. I was teaching physics around, teaching private lessons. Sorry, 1 minute. Teaching private lessons and the like. Sorry, I have my little boy.
It's fine.
All right, so in those situations where I have to teach, you know, I had the student that was teaching A levels, then private lesson. I would go to their house, teach them. They were paying me, I think, then 1,000 naira per hour, and these guys just wanted me to teach their kids. You know, they were looking for someone in the department who could help them teach their private lesson and the like. And then, you know, I was able to make some money, add some money to it, bought my first laptop. You understand? So when all my other kids, friends, colleagues, and they have their own parents buying laptops for them, for me, I have to work and buy my own laptop. And more scholarship came. I got another scholarship that gave me a free laptop, gave me 200K. I think they were paying 200K every year or something. And then, you know, little by little, those things started coming in. And my master's in UI then was also on scholarship. So I did it on scholarship. They were paying us 25,000 naira per month then. So I was collecting 25 around free accommodation, free everything. So I was able to do radiation and health physics, which is what I really love then. And when I finished, went to NYSC, you know, they started paying, I think, how much were they paying? 20, was it 18,000? I think we were collecting 18,000. 1908, was it 1908? Yeah, that was in 2013.
Okay. Wow.
Yeah. So, and then, you know, during that time, I actually wanted to be a lecturer. I had that dream that I want to be a lecturer. I want to lecture at the university. So I knew I was going to do master's, do PhD and the likes. But when I finished my master's in 2015, you know, those opportunities were not really coming. I started applying to schools. And I felt Asia should be easy, right? I wasn't really thinking about US. So I was applying to China, Korea, Japan. I was applying to all those national government scholarship, all those MEXT scholarship. I even applied to BA scholarship, wrote Nigerian FSB, or wrote exam. I was pretty sure I passed all those things. Till today, I've not seen the result. It was later that you just hear that some people were selected and they've traveled to Russia or they've traveled to Ukraine or some of these other countries that have bilateral relationship with Nigeria. Be a scholarship, or they've traveled to Mexico, they've traveled to blah blah blah. So I was just applying to all those things. They were not forthcoming. And one of the things that I thought then was that my first class, I had the first class, so it should be easy to get this scholarship. But I was very, very, very wrong. Then I was teaching. I started teaching in a secondary school. First class, masters. I was teaching GS2 students. You understand? I was teaching GS2 students. I was teaching them the GS2 and GS3. No, I think I was teaching GS3. So they split them into the basic science to physics, chemistry, biology. So I was teaching them the physics part of it. Of course, I love my students. They love me. I still have many of them today. Some of them who are graduates already. I have them as students today. My wife still spoke with one today who is in another country studying outside Nigeria too. She's studying medicine. So we have a lot of them, made me connect to them. But I love my job. I was teaching well. And from then, I was upgraded to start teaching A-level students. So I started teaching advanced level students, Cambridge advanced level. But then I was still making the applications. Now I was doing a lot of things in Nigeria then. I was doing conferences for students generally. We hold conferences. We do conferences 3 times in a year, so we gather in a place and a venue. Students from different schools, University Ibadan, Polytechnic Ibadan, they gather. My mindset majorly was secondary school students because I love secondary school students. I just want to impact them and so we do conferences, we do magazines, we give them magazines freely, we feed them when they come. They must eat food. Kids, the program is usually long, like 10 to 4 p.m. or 5 p.m. So we must keep them in between. So we do all those things every year, like 3 times or 4 times a year. We did that from like 2015 till I left Nigeria, actually. But I was teaching in secondary school and I continued to apply. I was applying to different places. I think it was 2017 or thereabout that I started shifting attention to US. I wrote GRE. The first time I wrote GRE, of course I passed it. Then I made applications. One school gave me admission without funding. I was almost paying for the I-20 to get the I-20 shipped to me and the likes. But eventually I didn't do that because I felt my wife was pregnant at that time too. She would give birth to our first child, and then I would miss all these things. And then I'm not even sure how I will get the tuition. Why should I use somebody else's statement of account when I'm not sure of the tuition? I just forfeited the whole thing. I wrote TOEFL in addition to my GRE. Then I applied to more schools, and that was how FSU came. And the funny thing about FSU admission is I applied to them the first time, and they didn't give me admission. So the second time, I was applying to a lot of different schools. I made up my mind I would apply to more schools. And then I wasn't going to apply to FSU. One day I was just doing my devotion. I came back from work. I was doing my devotion in the afternoon. I was at home alone. My wife, I think she was at work then. And then I was studying the scripture, and then I just had something in my spirit, like, where you were rejected, you will be accepted. And I just knew immediately that this is FSU. I just started saying, no, I'm not applying to FSU again. I was saying that out to myself, like, no. But I wrote in my diary, okay, to apply to FSU. I wrote it tiny, so that nobody will see it. I will be the only one to know what I wrote in my diary. Like, where you were rejected, you will be accepted. Then apply to FSU again. And I wrote somewhere there that if this $30 go to waste, Lord, I use it as a burnt offering to you. But interestingly, I added FSU. I told my friends that we were applying together. They were also rejected the previous year. I told them I'm applying to FSU. Those ones said, no, we are not applying to FSU. I'm not. So I applied to FSU. And FSU gave me the admission with funding. And the interesting thing was because I wasn't even really confident in the application. So I didn't send recommendation letter. I didn't send a new recommendation letter because I didn't want to disturb my recommenders to send to a place they have sent to before. So I wrote FSUL people. I told them I applied there last year. Can you use the same recommendation letter that they sent last year for my application? And they said, yes, that's fine. So far it's within 1.5 years because that's what I read in the website, some of the stuff. I think I also did not do something. My SOP, I changed my SOP. The previous year I got an advisor who said he would be my advisor. But this time around, I didn't bother looking for any advisor. I didn't bother to do anything. I was just like, I'm only applying because God led me to apply. So let him take care of whatever. And I applied, and before you know it, I got that admission, and then I found myself in the United States. How did I choose nuclear physics? Actually, I was going to choose condensed matter physics. That was what I was going to do. But I started listening to those talks, different professors will come and give their talks and all those things. And then I listened to my advisor talk about the nuclear physics stuff they do. And I felt like, this is interesting. Like, why am I even trying to go to condensed matter? Like, let me go to nuclear physics. Of course, it's related to the radiation and health physics, which I've done in my master's. And I felt, okay, let me go back home, let me do nuclear. Started doing it. That was it.
Oh, wow. That's quite a journey. Why did you?
Yeah, I find the journey very, very interesting, and congratulations! You finished another very huge milestone in the journey. Yeah, so let's quickly go to your science now. We want to discuss science. So in most of your papers, we noticed. So we reviewed some of your papers, right? And we noticed that you seem to be exciting elements on the periodic table. Is it like, so what does this mean? And is it like you just randomly pick an element on the table, and what do you do? What do you mean by excite? Do you make them happy or what? And why?
Okay.
Yeah.
So basically, what this experiment is, we want to understand the excited states, and what we mean by excited states are states that have high energy levels. Okay. Now, what in the nucleus can be in the ground state, and then they can, when they receive energy, they can move to the nucleons. When I say nucleons now, I mean protons and neutrons. They can move to a higher energy level. The same thing happens in the atomic model. Okay. For example, the way we see production of X-ray is because an electron moves from, what they call the SPDF shell in atomic model, where you have different circles, and they taught us that in chemistry in secondary school.
Yeah.
So if an electron moves from one, let's say K shell to an L shell, or vice versa, whichever way, X-ray can be produced. Either the X-ray is produced or the X-ray gives the energy. So, or the photon gives the energy. So in the nucleus, the same thing happens. There are different energy levels. So gamma rays let me just use the word this way. Gamma rays can cause an excitation of neutrons or protons from one level to another level. So let's say their energy levels, or if a proton or neutron, when there is a reduction in energy level, let me use that word now.
Okay.
When there's a reduction in energy level, just imagine I'm drawing lines.
Okay.
So the energy level reduced from this point to this point, gamma rays can be produced. So when they are excited, that means the energy is at high energy level. They are not properly stable. Let me use that word.
Yeah, if someone is excited, they're bouncing everywhere, right?
They're bouncing everywhere. So when we say stability now, the way neutrons, or the way radioactivity occurs is because the elements are not stable, right? And then they are trying to achieve stability. So they start emitting particles. So this way to this excited state, they are unstable state. Let me use that word. it does not fully define it, but just for the general.
Just for a general.
Yeah. They are unstable and they give out particles. They give out element. They can give out alpha particles, beta particles. They also give out gamma radiations.
So imagine if we have like an excited atom now.
Yeah.
You say in your paper you say we achieve a new spin state.
Yeah.
Why is this important to me, to Wale, or probably to my grandma that doesn't know anything about physics?
So basically, when you go to the hospital, for example, and they want to treat, let's say, okay, let me even start with what is common, what most people have done, X-rays, right? The way X-rays are produced is because an electron is shifting from one energy level to another energy level. And that's the way X-rays are produced. And the energy of the X-ray will be the difference between the two energy levels where the electron is moving from. Okay, so that means you must find a way to excite atom and then be able to produce that kind of the excitation. That is the way X-rays are produced. That means every time an operator of an X-ray press anything, it's trying to create a reaction that quickly does that thing and then produces X-rays.
Is it electricity that triggers this reaction or what?
No, not electricity in that sense. They are the reaction I do, they are nuclear reaction. So let me give you an example. Particle accelerators, that's one of the questions you asked here, right? So you have an accelerator that can accelerate particles. Okay, there's a way these are produced. I won't go into the details. There are different technical things. We call something cesium sputtering. Is a way to just think about ionization, okay, and then the way you get that ions you are interested in. So it's the ions of the particle that you accelerate at a very high speed. So the particle accelerator.
Is it by rush of wind? Or I'm just trying to how these things are moving at a high speed. Is it by wind?
So there are different things that you can use to do this. Magnetic fields are involved. Okay. And then, you can't really, when you think about these particles, start thinking wave particle dualization. Okay, because that's the way they travel. They are particles, but they can travel as waves.
Okay.
Right. So start thinking of, the accelerator, for example, we have a tandem accelerator. So in the tandem accelerator, there is a magnetic field somewhere which is positively charged. If the ion is negatively charged, you expect an attraction, right? So you expect that the ions are attracted. And of course, there are magnetic chain around the what do you call it now, the tandem accelerator, which also can generate some electrostatic. It's a combination of electric field and magnetic field in all these things that are going on. So just think it that way. The simple picture is just to think it this way, that particles are accelerated.
Actually, before we move to the next question, sorry, Dr. Ajayi, I have like a general question. I remember that when I was trying to go into science, I was taking physics. Then one of the things that scared me away from physics is that quantum physics or quantum whatever they call it, where they wrote all those things. Is quantum physics and all those equations that they write in quantum physics really related to what you do?
Yes, quantum mechanics is very much related. So if you remember in quantum mechanics, you deal with Schrodinger equation where it talks about the particles, where it talks about the energy. You have the wave, the potential of the particle. And then you want to get the energy, eigenvalue, eigenvectors, then eigenstates. Okay, so that's what we deal with. The eigenenergies, for example, are the energy levels which we are dealing with. Okay, the eigenstates, of course, they are the states. You mentioned the states mentioned spin the other time. Each levels have their own states. We call them states. Okay, so those eigenstates belong to each of those levels, and then the relationship with all these things give results to some of these things we are talking about. So in fact, some of these things can be modeled with the Schrodinger equation. So different potential wells, you draw different potential wells or different type of potential to be able to model the movement of the nucleus. So, for example, this is too detailed, but the potential that we use in solving the Schrodinger equation is the Wood-Saxon potential. That's what we do. People started from the, I'm going into details, okay. So, but basically what we are doing is this. If you remember, let me try to bring it down a bit. If you remember when we talk about stability in nucleus, or you remember, the atomic picture, you say some elements are stable. You talk about helium, you talk about some noble gases, right, that won't react. They have their own properties because they are stable in that sense. In the nuclear picture too, we adopt that type of stability. Some nuclear that are stable. Okay, and remember they have their own combination of proton number and neutron number. And then we have what we call magic numbers. I think we did it in chemistry those days too. We have what we call the magic numbers, and nucleus that have this magic number have some properties of stability, some exceptional stability. Their binding energy is very high. It's very difficult to break them apart. Their neutron, their SN, the energy needed to pull a neutron or proton out of them is very, very high. So they are stable. Basically, that's what I mean. So you can model a Schrodinger equation and then get this magic number and then give a, what do you call it now? A potential that generates this magic number, that generates the number of neutrons and protons. So it's very related to quantum mechanics, basically. But those who work early from the theory part, you start from the quantum mechanics and they're solving of things, the generacy, the eigenvectors, eigenvalue, we are doing the what do you call this thing that we do, the Brian Kurtz, all those things. I don't know if you did all those things, and yeah. So the quantum mechanics, you deal with all these Brian Kurtz, the expectation value and all those things. We deal with all those things. So basically, that's part of the theory part, which helps to model it. But how does it affect people, basically, right? So, for example, so I'm studying nuclear structure. My part is nuclear structure. There are those who do nuclear reaction and the like. When you understand the structure of a nucleus, for example, and say this element in the periodic table, like Wale mentioned, as if you only look at the paper, you will see new energy levels that we've discovered and all those things. So you can say, so this nucleus has this gamma ray coming out from it. That means, number one, you can identify that nucleus by the gamma rays coming out from it. So let's say, for example, a terrorist is coming with a very terrible material to come and destroy people or kill people or whatever, and then you're able to detect those material by the gamma rays coming out from the material. So in forensic, you can use it in that regard to safeguard the security of a nation and say, oh, this material is radioactive. You can use your detectors to detect it and say this energy line that we are seeing belongs to uranium. This energy line we are seeing belongs to this and that. Remember, what's the problem in the world today? Uranium-238, uranium-235. If you enrich uranium-238, you get uranium-235, which is a dangerous one, which is used in nuclear bombs, even weapons and like. You don't know the lines coming out from uranium-235. You cannot discover it. You can't detect it. So you need to be able to know. And sometimes some reactions are needed to be able to get this element in an excited state so that it can release gamma rays. So sometimes neutron activation is what some people do. If you have a material somewhere, if you shoot it with neutron, it gets excited. And in the process of getting excited, it starts emitting gamma rays too. And then you can look at the gamma rays and say, let's say you excite, let me use an example, 14 carbon, for just a random example, 14 carbon you shoot a neutron to it, it becomes 15 carbon, and then it starts de-exciting. Then you should start seeing lines, gamma ray lines from 15 carbon. Then you can know that this element that I dealt with is 14 carbon. Because you are seeing lines from 15 carbon. But why are you seeing lines from 15 carbon? Because neutron has a mass number of 1, right? And then the atomic number of 0. So shoot it, and then you get 15 carbon. And then you're able to see, oh, this thing is 14 carbon. So it's useful in that way. Even in hospitals, for example, the treatments, radiotherapy and the likes, we use cobalt-60 for treatment and like you must be able to know. Of course, you can use that. You can identify what these things are. The gamma lines that come from them, you use to identify them. Then you need to know the energy of the gamma rays, right? Because you need energy of the gamma rays, what you need to kill the tumor cells, you need to kill all these things. If it's too much, there is problem. If it's too low, it will not be enough. So you need to be able to find a way to measure. So everything we are doing, nuclear structure, is to understand what the structure of the nucleus looks like.
I see.
Basically, what the structure is. So we are trying. So excitation is a way of, if you do a surgery and open human brain, right, you can see what's inside. But excitation is a way of not opening the brain, but still just shooting the brain with something and then see what comes back. And then you're able to say, oh, from what comes back, what is we are seeing, this is what this brain looks like, basically. And it is the properties you see from this nucleus that determines what their application will be. So some of the applications will be in medicine, some will be in forensics, some will be in energy generation, because for you to generate energy too, you must know, okay, finding energy of this thing, what is all these things, what are the energy levels there, what is the cross-section of the interaction, what is all these things. Cross-section basically means what is the likelihood that the interaction will occur, or the probability that the interaction will occur. So all these things that you are calculating, and it's all part of the nuclear physics. That answered the question, at least.
Yeah. To a good extent. I mean, it's a complex topic, so I think you are doing a good job by breaking.
We use different complex methods to do what we are doing. So basically, some of those methods may not make sense to someone outside of the field, right? You talk about angular distribution, you talk about polarization, you talk about all these things that we do. You see different graphs, different weird graphs and the likes.
Okay.
And just like we always compare with theory. Okay, remember I said theory can predict too. And then what we also want to do generally is to be able to build a theoretical models that we can say, okay, these theoretical models can be used to predict what the energy levels in this nucleus look like. But what eventually one wants to be able to say is that we are calculating the strong nuclear force that holds nucleus together.
So just a question before you go to two questions. So you talked about the strong nuclear force. Is it so? I'm not saying you should create bomb, but I have a question about bombs. So if you are able to separate this force, is it the amount of energy it takes to separate them that makes it a stronger bomb?
Yeah, so there are people who work on research that deals directly with bombs anyway, so there's no denying that. And majorly they are fission reactions.
Okay.
So the way the fission reaction starts, remember you need a fissionable nuclei. Okay, can fission.
Fission means break down or separate.
Separate, yes. So it separates into, so you have, let's say, a neutron, you shoot a neutron on a fissionable nuclei, for example, you run on 235, it breaks into two, right? Almost equal two parts. It produces energy. It produces more neutrons, like 3 neutrons, for example. The original uranium is still there. The 3 neutrons act on the uranium again. Each neutron produces 3 more neutrons. Uses energy. That's like 9
reaction.
Chain reaction, exactly. So you have like 9 neutrons, right? Then the see, because I'm raising my hand. Oh, okay. So the each of the 9 neutrons again reacts. Each of them produces 9 more energy.
I see.
Radioactive, the neutron themselves are radioactive too, right? They can destroy. They are ionizing radiation. Okay, neutrons themselves are ionizing radiation. So you produce more. You are producing more neutrons, more energy, and then it's radioactive, and it continues on and on and on, and the energy just keep producing. And this thing does not happen in, let's say 10 minutes. No, they happen within seconds. Wow. Okay, so the time scale which we do deal with in reaction are like 10 raised by minus 22, 10 raised by minus 19 seconds. So you can imagine what will happen in 1 minute after you have such a thing happen. And then it just continues that way. And you have a lot of neutrons and the ionizing radiation. Ionizing simply means they can displace cell in your body. They can ionize. So, for example, if the ionizing radiation comes into someone, it displaces the cell. Cell is destroyed, or is not destroyed is what? The cell is displaced. The cell tries to repair itself. And in the process of the cell trying to repair itself, some of the cells will not repair correctly. Mutation can happen. I imagine many highly energetic neutrons bombarding people. Such continues on and on. And because of the fission process taking place, the chain reaction, the energy produced is huge. But it's almost the same process in a nuclear reactor too. It's just that in the nuclear reactor, you have a way of controlling the neutrons that are produced. So you can absorb every 2 neutrons out of 3 neutrons. Absorb 2. We have the carbon rod, which is used, and some other method, heavy water and the likes. Doing that.
My second question: Oppenheimer or Big Bang Theory? For you, maybe you don't watch movies.
I mean, I know Oppenheimer, yeah, but I've not watched Big Bang Theory. I know it's very popular. I try to follow a bit. Then it's a long series, so it's because it's really long. But yeah, if talking about the events themselves, if I should choose between the events themselves, because Big Bang Theory has a lot of implication for the world too, because it connotes the beginning of the universe, which has lot of implications. I'll go with Big Bang. I mean, I watched the part of the Big Bang Theory. It's funny. It's a comedy series. So I think Oppenheimer as a movie is very serious. It's a very serious.
Okay.
So I'll go with Big Bang Theory. Yeah.
Okay, interesting. So we have to. We are already running low on time, but yeah. So I want you to walk us through the paper where you work on the collective modes of excitation of cobalt, nickel, and cobalt 59, nickel 59, and cobalt 61. So first question is, why are they interesting? And what was the scientific process like? How did you come to selecting this set of elements? And what was their initial hypothesis like? Did you expect them to give you something before? And when you did your experiment, what was the experiment like? And did you validate the initial hypothesis? How did you interpret it? Something like, take us through your work in the lab.
Okay. So basically, in choosing what to work on in nuclear physics, nuclear structure, for example, you want something interesting, right? Remember, I mentioned from the beginning that there are theoretical models that models how excitation works in nuclear. And I gave a simple example of people with solved this Schrodinger equation. You can come up with the excited states, right, of nuclear. You can predict how nucleons are excited in the nucleus, where they move from one energy level to another energy level. Now, the problem is, as you have more neutrons, not more nucleons, more neutrons and protons, as they become more and more, the situations become complex. No, even in the nucleus themselves. Remember, you have proton on this side, neutron on this side. We have what we call shells in which they can fill. You have the SD shell, you have the S shell, you have the P shell, you have the SD shell, you have the T shell, PF shell, on, which they can fill and they can move differently. And those gaps that you see, if you type in Google now, you type shell model, and then you type to see images, you will see those shells that it will bring out. And those shells have different spacing, which talks about their energy differences. Okay? So as more neutrons are produced, or let me use the word, as you have more neutrons, as you go higher in mass number, it means you have more neutrons and more protons. The excitations become more complex, of course, as expected, right? And what we always want to do is to be able to use experimental results to compare with theoretical models, so that theoretical models can tweak their theory, or those doing the theory can tweak their theory to align with experiments. So there's been a lot of experiments in the low line. In fact, from the SD shell, for example, there have been a lot of experiments done there. There have been perfect agreement with shell model. As you move ahead, you start seeing some differences in the type of excitation experimentally. Okay? So, for example, if you look at 56 nickel, it's closed shell, 28 number of protons, 28 number of neutrons. And what that means is that is pretty, because 28 is a magic number, and that means 56 nickel should be stable, right? If you look at 68 nickel on the other side, 40 sometimes is regarded as magic. It used to be regarded as magic number, but it's changing now. But at least 28 is also magic number, and then you expect it to be stable, right? So within these two values, or let me say within these 2 points, the elements observed, the nucleus observed there within those regions, they have their different characteristics. No, in stable nuclei, you expect them to have what we call single particle excitation, where you can just move one proton from one shell to another and say, oh, this proton, and then you say, oh, this energy level has this particular spin. But when you move within that shell, within that region between that 56 nickel and 68 nickel, the type of excitation looks so different. For example, you start seeing some type of excitation that you cannot explain with the single particle excitation of just moving one proton or one neutron from one shell to another. You can't explain it again. And then you begin to look for another way of explaining what is going on there. So that region is very interesting because of those things that happen there. And that region is where we see the formation of the nucleus, so to speak. Now, the shape of the nucleus is expected to be spherical. There are some things we observe from the excitation that points to them as not spherical. Sometimes maybe a bit deformed, or looking like the shape of a prolate shape, looking like the shape of a baseball or American football. So instead of it being spherical, then it's being squished this way. So those different interesting phenomena happening in that region makes it interesting. And because we want to see what the excitation pattern looks like experimentally, we want to be able to pinpoint the energy level. Then we compare to theory. And when theoretical models, if they're able to match our result, they have to tweak some parameters in their calculation to be able to match this. And remember, the whole big goal is to be able to have something to generate the nuclear force, right? Then all these little steps contribute to the big goal. So, and that's why you see us adding new energy level, new lines that we can add. In the paper, you will see everything in red. I identify them as new. They are new lines. Of course, you have to establish the everything you see in black is what has been done before. So you establish those black results and say, oh, they are there. We can see what people have seen before. Then you see new things, you add the new things which you have done. So that region is very important because of that phenomenon which I've talked about. And of course, different regions have their own specific interesting things. So there are people who are working on lower level region, let's say less than 20, maybe around 20. A equals 20, atomic mass equals 20. There are those working around atomic mass equals 80. Some are even working around atomic mass equals over 100. Okay. Now, when you see those who are working over 100, it goes into some thing that has to do with fission, nuclear bomb, which we've been interested in. So people who are working in those regions, there are some of the things that they see. I have a colleague who is working on nuclear fission actually. But as an international student, I can't work on nuclear fission, right? Except until I'm a citizen, then I can work on certain. Even in some labs now, if I go to some labs, I can access some areas. I need security clearance to access some areas. So different region based on different things that people are really interested in. That's why we choose that region, because of those interesting phenomena, which we want to be able to compare with theory and allow theory to gain from us too. And then when theory gains from, it becomes like a cycle. We do, theory does from based on what we have done. Then we look at their calculation again. We use it for another region. We continue that cycle.
Yeah, I think it also makes sense. Some of the things I saw in Big Bang Theory, they were like arguing between theory and experimentalists.
Yeah.
Okay.
So from a scientific point of view, like you just said, you as an international student, there are some labs that you cannot enter. You need some security clearance and stuff. Yeah, I understand. Like, so can you like tell us how your lab is set up? Probably in your lab you probably have some machine that maybe it's not in any other country apart from the US. Maybe some machine I work with. I've not even seen it in Nigeria before. Can you walk us through?
Yeah, basically that you've seen things. I mean, the things I saw when I came, they were the first time I was saying that. I didn't say anything back to Nigeria. So we have a tandem accelerator, which I've talked about before. It's a 9 megavolt tandem accelerator, which can accelerate particles through 9 volts, then 9 megavolts rather. And then we have a linear. Yeah, we have a linear. Mega is 10 raised power 6. So you can imagine how high that is. If you want to think about it, think about the fact that you need how many volts, 110 volts for electricity to be transported, for electrons to move, right? In Nigeria, I think it's 110 volts, and then how many amps? I've forgotten how many amperes, but most of the sockets are 110 volts. So imagine now 9 megavolts. Can you imagine how high that is? Then we also have a superlinear conducting accelerator, which is an addition to the N9MV tandem accelerator. It also accelerates particles basically, with different principle from the tandem accelerator basically. So that is 10 MV, 10 to 12 MV, if I remember correctly. Then you have different detectors. Okay, so those ones are just to accelerate particles. You have different, because the reaction, the way it happens is when we accelerate particles, we hit it on a target, okay, and then we allow the nuclear reaction to take place there, and then you start seeing those different particles being emitted. So we also have different detectors, different types of detectors. I work basically with high purity germanium detectors. Those detectors are very expensive, very, very expensive. One detector can go for like 200,000. Okay. It's one clover detectors. One clover detector, like $400,000, $250,000. Some may even be expensive. And we have like in our array, we have like 10 of that. Array 10 of that. There are spaces for like 16. Okay. And that's what just my group works on. There are other groups which they have their own detectors, different detectors, big detectors. So in our lab, you see those big giant detectors, you see big magnets. Those magnets are to direct the beam, the particle that we accelerate. You can remember all this formula, mv squared over r equals qvb, all those things. You can use them to direct the direction of the beam. So we have all those giant magnets at different locations. We have a system where we'll be able to make all the beam lines to be in a vacuum. So we work in vacuum most of the time to be able to direct all these particles to be able to have a reaction takes place. So that's what you will see basically particulars, the accelerators and the detectors. Basically, every other thing is just things that help around with that, the magnets, the vacuum system, the electronics. You have the electronic system because you need like a digital to analog to digital precision system and all those things you need to do all those things. Of course, big computers, the computers that are used to do all these calculations. You have some theory folks who have some super computers in code to be able to do all these calculations. The calculations will run for days and days and days. So because they need very high powered computers to do all of these things too.
Yeah. So I have another question that is very general. I know now you work on radiation, nuclear stuff, and from my simple knowledge, I know that some of nuclear stuff they can cause cancer and stuff like that. Do you have to wear like big jackets and stuff like that to protect yourself? Or
okay, yeah. So not necessarily. Also, we have dosimeters which you must wear in radiation area because we must calculate the radiation that you receive to your body every like quarterly, so that they know if they will pull you out, so you don't have to be there for some time or not. But the radiation generated in our lab, basically, they are not the intensity. They are not very damaging in terms of intensity, in terms of what do you call it, activity. Okay, so for example, we have sources that are like let's say 1.5 microcurie. Okay, and I think 1 Curie is 10 times 10 per 1 times 10 per 10 disintegrations per second, basically. So there are some of them are very low in activity, so which means we can still cope with it. Of course, when there is an experiment going on, the target and all those things that are used become radioactive, and then we won't go near them immediately. We wait for them to cool down. Some of the radiation, alpha radiation, for example, they can get stopped by your hand. Just your hand. Alpha radiations can get stopped in that way. But of course, we still generate some neutrons, gamma rays travel faster and the like. But the activity from the sources are not so high. And then the energy from these things are not so damaging in that sense. We don't generate, let me use the word deadly radiation. Let me use that word. But of course, we still measure them, okay, just to see what we come in contact with. Of course, when experiment is going on, there are radiation areas where you don't want to go into. Okay, so you don't go into the except the beam is stopped. Those radiation, when those experiments are have more radiation being generated. So when someone is in, we have a system where if anyone wants to put in the radiation, wants to press go, let me just use the word. We announce in the mic like, please leave the radiation area, blah, blah, blah. If anyone is in target from 1, target from 2, please leave. And people have to leave before you press it in. So those are the safety measures. In fact, there are interlock system where if the experiment is going on and someone breaches a door,
okay,
radiation will stop. Okay. So that you don't go into the radiation area because the experiment is on. So everything is stopped. So basically, there is a system in place. But aside that, the general radiation in the area when the experiment is not on is something minimal, something we can. Yeah, we all receive radiation whether we like it or not. Someone who has gone to do X-ray probably has received more radiation than me staying in.
Exactly. Yeah. Yeah. So the last question I have from this part is, now I know that you don't create bombs, right? But you have been mentioning particle acceleration, radiation, and all of that. And imagine you didn't do your PhD in Florida State. Imagine you did it in the University of Ibadan or you did it in OAU. Do you think you still be exposed to these kind of things, or you just be things on the surface level?
Oh, definitely, I won't be exposed to this. I mean, I've visited different labs here to do experiments, and what you see there is mind blowing compared to what we have in Nigeria, right? So it's mind this difference, the scale it's too wide. You can't just compare it honestly. the first time I saw an accelerator is when I came here. I only saw it in movies. I think I've seen it in a movie before. But when I came here, I was looking at it physically. I even entered the accelerator. I have a picture of me inside the accelerator because it's big. So I can enter inside and stand inside it. I jump. I can't remember if I can jump. So it's very high, right? So in Nigeria, we don't the nuclear physics. We don't. Let me just say that we don't really have the nuclear physics research in Nigeria. Basically, I know there is one research reactor which is in, I think, Abu Zaria, that is to be used for training. I don't know how active that is, but I know it's a research reactor. It's just to train. And I know there is a 1 MV tandem accelerator, I think, in OAU. I think that one is for medical purposes and then like. And you know, hospitals should have accelerators, right? Hospitals to generate. Remember, I mentioned that all these things work. It's a reaction that happens for these things to be produced, right? So in producing radioisotopes and all these things that are used, these things should be used. I know there is 1 MV, we use 9 MV to do our reaction. There is 1 MV in OAU, I think. It's a very small one. I think I don't know if it's active, if I can search now. I don't know what they use it to do. So, but if I have been in Nigeria, I don't think I would have been exposed to this thing I'm doing now. Because even the radiation analysis I used an alpha guard radon monitor to be able to do it, and that was gotten from Germany. It was newly gotten when I started doing it then.
Interesting. Okay, just we have more time. Okay, let's go to the nuance window. The nuance window is just a space for you to say anything within 2 to 5 minutes, to freely talk about anything on your mind with a broad perspective, right? And you can comment either on your science or your nuclear physics or the next bomb you want to create, anything to your government, to Nigeria, to Africa, or generally any lessons that you think.
Yeah, sorry. So the 1 MV as 1.7 MV I was talking about is at the Center for Energy Research and Development of Obafemi Awolowo University. So, and then when it was commissioned, they said in a bid to acquire a nuclear power plant for the country. And I'm wondering, with 1.7 MV, for goodness sake, what are you guys thinking?
Let's keep this part there. So all right. You can just talk about the nuance window and anything on your mind on any broad perspective with science, governments, humanity, sports.
Yeah. So generally, I just wish Nigeria can take education seriously, take research seriously. It's a terrible thing when we don't have the research facilities and researchers have to fly to other countries to do research, or they have to send samples to other countries for them to measure something as basic as anything. Like, I'm not sure how much facilities in Nigeria to even measure some simple radiation sample in Nigeria, which is very terrible. Go to South Africa, for example, they have accelerators. They have a center. There is a lab there called Itembas Laboratory, which is a very big lab. They do this kind of research we do here in the US. They're in South Africa, and it's amazing. We'll say Nigeria is giant of Africa, but we can't do all these things, and it's terrible. And the first thing that we need to be tackled is electricity, because some of our experiments run for weeks. We are running weeks, and then electricity must be there. On my phone, I receive updates of things going on in school. On my detectors, I just receive alarm from there. So that means they must be on 24/7 network connection to be able to send me text messages from my phone at any time of the day from anywhere. I can connect to the computer in school with my phone and control things. If something is going bad, I can more check it from my phone and control it and press some commands. And then if you do it, it will respond in school. All these are taking place because There's electricity, there's internet connection, the connection, everything is made perfect. And even me, I have internet connection where I am, and I can log to the computers in school. So if all these things are not in place, I don't see how research will advance in Nigeria. And if research is not advancing, then technology-wise, we are also not advancing. And that's why we remain as the third world country that Nigeria is today. If all this is not in place, you can't expect people to come back. The government says to people, come back home, come back home, come back home. To do what? Okay, where is the research facilities? To do what? What research? Like, what will I just join the other lecturers and just be teaching and no research? Or I will just say, okay, now let me just be doing the low level research that everybody is doing, or I'll start doing research and start waiting for electricity or something. Or where do I mentioned one of our detectors is $200,000. So that means if you have 10 of that, you are spending $2 million, right? On just an array of detector. Yeah, and that's not even talking about all the other accelerator, which are even way more expensive, millions and millions and millions of dollars. If you check how much funding goes to education or to research here in the US, you'll be seeing our lab, for example, got a grant of $9 million, right? For 5 years. And that's how labs are getting it. Some labs are getting 10 million, this million, this million. So the government is spending billions of dollars on research in the United States. And in Nigeria, we have our president, our governor, the vice president. They'll be spending billions of naira on their own house, on their own buildings, on renovation. They are saying they're spending billions of dollars. It's heartbreaking. It's heartbreaking. Look at the hospitals too. I complained recently about radiotherapy in Nigeria. We don't have anything to use for radiotherapy. We have maybe, I can't remember how many it is then, but compared to other countries like Egypt, South Africa, they go way ahead of us. One single state, but one single university may have more accelerators to use than its whole Nigeria. I give an example of Texas. They have more than the whole of Nigeria. So it's very heartbreaking, all those things going on. I just wish something can be done. I don't know, with the current set of leadership, I don't think priority will be given to it. But all they want to do is steal money and then bless their own family and lives, then leave this as well.
Yeah.
Yeah. So there was a question about how Nigeria can harness your talent, and I think you have indirectly answered that question.
Yeah, because what do they want me to do? If they say, okay, come and add the isotope in it, the isotope, what funding are they putting there? Right?
Yeah.
So I'll just sit in office all day long, signing papers and doing what? What do you want me to do? So it's very terrible. It's very terrible. We have NNRA in Nigeria, Nigeria Nuclear Regulatory Authority. All they do is calibrate devices for those working in the oil industry. That's because, of course, they use radiation in the oil industry. They calibrate their devices and the likes. I don't know if they do any other special thing in quotes. They'll say, oh, mining area, we are monitoring radon, blah, 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 blah. I met a professor. She's a top professor here in the United States. She's from Armenia. And she was appointed by the Armenian government to be able to help their radioisotope production unit for PET scan, PET scan, for cancer treatment, diagnostics, and the like. And Armenia was able to do it. Armenia, a physicist headed it. I know the professor, I met her, we spoke at length, right? Those times she would tell me, I'll message her, she would say, oh, she's out of the country, probably in Armenia. I've seen, if you go to YouTube, type her name, you will see pictures or videos of her with the president of the country and the like. Those are serious countries who want to eradicate cancer. Now, a lot of cancer cases in Nigeria now, we don't have centers equipped for some of these things. These are the benefits of nuclear physics. We have to be able to produce radioisotopes, right, to be able to counter all these terrible diseases. But they are not putting money there. They are putting money somewhere else, in their own pockets, in their own stomach. It's terrible, honestly.
Yeah, I hope that Nigeria gets to that point where they will prioritize major in the, like, they have to major in the major and not minor in the major.
Exactly.
I hope they get to that point one day.
See, the thing is,
So
there's corruption everywhere, right? That's
yeah,
what we see.
of
But
course, yeah.
again, the level at which is happening in Nigeria is that level where they say we don't care about the citizens, right?
It's
The corruption,
exceptional.
yeah, the corruption in or some other country is like, or maybe someone has an inside information about a company, then they quickly invest there. In Nigeria, that's even almost normal, right? The corruption in Nigeria is someone say this money, 80 billion, belongs to pensioners. And the person say, yes, but I'll put it in my pocket. And the citizens will do nothing. And then EFCC will say, oh, we take you to court. They will now say, we are out of the 80
Bill,
billion, pay 1 million bill. And then the case has
that's
ended.
it.
That's it. See, yeah, bill now. Yeah, all the money from Kogi State, he just took everything. The money
The
that
one that always vexed me is Dino Melaye.
yes, and they will be putting that wealth on social media, showing it
Yeah.
that we can do anything.
You cannot do
This
anything, yeah.
there was a tweet I made that showed the money. I can't remember who stole that money, and I was breaking down how many things that this money can buy,
You can do, yeah.
how many firefighters this money can buy, how many. I think it was the Minister of Aviation said how many billions did that one steal? I can't even remember how many.
Adi Sirika.
The billions are just there. They're just stealing it, stealing it, and we can do a lot with this money. Build hospitals, equip the existing hospitals, not even build new
Exactly,
Yeah.
ones. And people are dying every day. It's painful, honestly.
yeah. So it's hopefully Nigeria gets it right, but I don't think it's going to change anytime soon. But my last question is industry or academia, because I know you love teaching.
I love teaching, honestly. Honestly, love teaching. Academia, yeah, academia. I mean, it's based on what's going on with me currently. Academia, there may be a bit, but not fully industry. I also love the regulatory part of it because my advisor used to be in Nigeria, Professor Farah. I had some bad news about him recently. But I'm not, I don't know if the family is announcing yet, but Professor Farah used to work in Nigeria Nuclear Regulatory Authority. And then that made sense. The US has Nuclear Regulatory Authority to NRC, which makes I won't be in the industry of just production of chips, blah, blah, blah. Not really what I'm caught more for the academia, honestly. But you may hear later that I went via regulatory, still find my way back to academia because of the way things are currently going on in the United States, funding and the likes.
Yeah. Hopefully, I pray that God will guide you and direct your path and make you make the right decision. Yeah. We are so grateful for having Dr. Ajayi on our podcast today. And we are so glad that you accepted our invitation, giving your time. Did you have any other thing to say?
Nothing, just that to appreciate Dr. Ajayi, and he's very humble with his explanation.
You know that it's called to be a teacher.
Yeah, it's called to teach you. Yeah.
No, when I was giving my defense, my wife was there, and then after the thing, my wife was like, "Have I finished?" I said, "Yes." Now she said she's only in excitation; she does not understand anything. And I was saying that, but I was trying to bring it down to as
your level
as possible.
She's in biology, right?
She's in pharmaceutical sciences.
Oh, I think excitation will be hard.
But I understand that risk because she's dealing with the health of people directly. Is what I can see. Like he's trying to deal with Alzheimer, Parkinson's disease, and the likes. Those are the things she's working with.
That's nice. All right, thank you everyone for joining us today. We'll see you some other time.
Bye for now.
Bye.